All right. Good morning, everybody. We'll go ahead and get this webinar started. All right. Thank you, everyone, for joining us today in our webinar in additive manufacturing processes. We look forward to sharing with you our vision for the future of additive production manufacturing. Over the last several years, we've all been told that additive technologies will change the face of manufacturing. And today, we find ourselves at the tipping point of that movement. GF Machining Solutions has been making purposeful strides into additive workflow, and we are pleased to present to you our solution for vertical integration into this segment. I'm Lindsay Lewis, Head of Sales for Advanced Manufacturing North America at GF Machining Solutions. I lead a team of 5 regional sales managers covering our entire advanced technologies here in North America, including laser ablation, micromachining, and additive manufacturing. Before we get started, I wanted to note that we will be recording this webinar for future viewing purposes. From here, I am going to allow my energetic North American advanced sales team to quickly introduce themselves. John Boring, I think we'll have you take the lead.
Good morning, everyone. My name is John Boring. I'm speaking to you from our Center of Competence for Aerospace in Huntersville, North Carolina, where we've actually got our leak teeth product line in addition to micron mills and everything else that we carry. At the end of the webinar today, we'll have some time set aside for Q&A. So if you have any questions, please type those in the box, and I will bring those up to Romain when we have a moment at the end of the presentation.
Perfect. Thank you, John. Salim, if you want to go ahead next.
Yeah, hi. So I'm Salim Gawad. I'm sales manager for advanced manufacturing on the West Coast. I've been with GF for a bit more than 5 years now. I started in Switzerland, then 3 years in Asia, and now I'm joining here from our office in Irvine, California.
Thank you, Salim. And John Carlson.
Good morning, everyone. Appreciate you joining us this morning for the webinar. Again, my name is John Carlson. I am the Advanced Manufacturing Sales Manager here, located in our U.S. headquarters here in Lincolnshire, and standing actually in front of the focus for today's webinar. So again, I really appreciate you guys joining us, and I hope we're able to provide you some quality information what you guys are looking for. Thank you so much.
Thanks, John. All right, so from here, I'd like to introduce to you our guest of honor, Romain Dubrulle. Romain has worked with GF Machining Solutions for 4 years, joining as an additive manufacturing engineer. He is today responsible for the business support to the GFMS sales in the field of additive manufacturing and leads a team of additive applications engineers. Prior to GF Machining Solutions, he was a production manager in injection molding of high-tech components. Romain, thank you so much for joining us today. If you want to begin, we will be honored.
Thank you very much, Lindsay. So here you have our colleagues in the US that will be able to support you. So our contacts are here available for whoever wants to ask any questions. So the topic of today will be how to streamline and optimize your metal AM workflows. To introduce the topic and to explain why we want to cover this subject, a few elements that and details that we could gather from the market. So the first thing is that today we see that AM is shifting more and more into production series. So metal AM was often used for prototyping or for small series. Now we see more and more it's shifting into production of larger, mid-sized and large series. And here, of course, the needs of production are very different to those of the very small series or prototyping. So in a production environment, AM users target a cost reduction of the technology, much more technology integration, and we will cover this in great detail, and a real reduction of manual operations when handling the production that you will have to go through. So also, one thing that is important, so often what AM machine manufacturers say AM looks like is often displayed as the picture that you have here, meaning that you have a perfect line of machines that are organized in the shop, and it looks like if you just put in a 3D model on one side and it comes out, a finished part comes out on the other side. However, if you look in reality, what AM production looks like, it looks a lot more like this in real for those who are using AM and in reality. So it's often very manual, it's time consuming, the results and the quality are inconsistent, and the post-processing equipment that is available in order to do this, to finish the AM parts, is often very ill adapted to the needs of AM. Another element, so actually here in Europe, there's a large conference that is held by Oerlikon, which gathers a lot of AM users, and actually there are quite a few live polls that are run during this conference, and there are two that caught my attention in the conference that took place end of last year. Basically, the questions that were asked is, where do we need more disruptive solutions, and where would we benefit from further acceleration into industrialization? And what you can see here from the results of these polls are that users of AM, and these are real users, so these are, it gathers an audience of 1,000 users of Metal AM, they believe that the needs are in integration of the process chain, so integration of AM into the process chain, and combination of printer and all the rest of the equipment that you will have in your shop. So these are the two areas where Metal AM users feel that there is a lot more to be done, and this is above. So you see here, so the integration into the process chain, it is above the needs in terms of disruption in the hardware of Metal AM. It's above the needs in terms of disruption in the materials for Metal AM, above the software. So this is really a need that users have identified and where they feel that there are solutions that are missing. So a quick word in addition to what is the definition and what we mean by automation and by integration. So often what is demonstrated and the idea that people have of an optimized production line is an automotive production line. So where everything is handled by robots and there is basically no human interaction and everything is done in a line. No? So you will go step by step in a production line. However, this is not necessarily correct. So if you imagine, for example, the production of an AM part, this will go on for many hours. Does it make sense to have a robot waiting for your AM machine to finish, and then for the robot to work for 5 seconds and feed an a milling machine, which will have a cycle time that is much lower? I'm not sure it does. So where we need to make more progress in terms of the integration is more in the design and optimization of the preparation of the data for AM, in the easy and convenient handling of the parts that are produced. So you don't necessarily need to handle them in a straight uninterrupted line. However, you need to make it easy to handle and shift from one machine to the other. You need to ensure a high OEE of machines. So of course you want your machine to be running as much as possible. And of course you want to do all these steps while maintaining the highest levels of quality possible. So this is where GF works on the concept of metal integration, and this relies on a number of bricks. So the first elements that you will have, and this is early on in the stages, are the software to design and prepare the AM parts that you will have to handle. Of course, this goes together with simulation tools, and this is more and more true in the world of Metal AM. If you have a very critical part, you will want to simulate this part before you go into the production. Make sure that you will not have abnormal stress, that everything will go through seamlessly. The second stage is really in the hardware. So this is, of course, and this is the core technology that we're talking about today, is the Metal AM hardware. This is the first step. However, in the case of Metal AM, a lot of parts will not, 99% of parts will not be finished after the AM step. So they will need to go through post-processing operation. So this means that we have to have bricks that work well together with the AM hardware in the post-processing equipment. It means also that you have to have adaptations in the CAM software for the post-processing preparation, because when you're handling AM parts, these have support structures, these have very, very particular geometries. These are not easy to handle on the CAM side. So you need to have an adapted CAM in order to work on this. And finally, above all this, and this is maybe the elements that will be the glue to make everything work seamlessly, is you need very efficient quality validation tools to make sure that you're producing with the highest standards of quality. And in addition, in order to be able to go seamlessly from the AM to the post-processing, this goes through tooling for the post-processing. So tooling elements that will allow you to move seamlessly from the metal AM hardware to the post-processing hardware. So in order to demonstrate a bit, up to now we have been a bit theoretical, and now we'll go a bit more in detail. And the best way to demonstrate that is going through two case studies. So the two case studies that we have here are the first case study is an implant. So this is a cervical implant that is a spinal implant that is used for medical devices. So it's produced by additive because it allows you to design very complex lattice structures that will allow the bone and the tissue to grow into. So that is the main advantage of producing these in AM. And actually, you may not know this, but the standard technology that is used in order to produce these kinds of parts today is AM. So these are really this is really a series production example. So here you can see where it goes into the spine of the patient. So here you have the overview of how we would treat this, and we'll go into the different steps of this workflow, starting from the very early in the design phases. So you need design tools in order to be able to manufacture these complex AM structures. You'll then prepare, print, inspect, prepare the CNC for these geometries, and then go through the machining operations. So that is our first example that we'll treat in a bit greater detail. The second example that we have, this is an aerospace bracket. So it's a lightweight aerospace bracket that is used actually on satellites. So here you see where it is mounted on the satellite. So it's produced in titanium. Its goal is really to be really lightweight, and it's basically used to mount the satellite dish to the core of the satellite in telecommunication satellites. So here again, we'll go through the work process that you have for this part, going from the design page all the way to the final part. So now if we dive deep into these two geometries, starting with the design phase. So here we have a very efficient solution in order to be able to design your AM parts. So we talked about the spinal cage. The spinal cage, this has a lot of lattice structures that are generated in here. What you need for this is you need specialized software. And so with 3D Expert, what we're able to do is to really design the part for metal AM. And what is interesting also is that we're working with a software that is in line with the industry standards, meaning that this is not only a mesh software, so you can really work with solid models and your step files that you're used to working with in industry. This is also the stage where you will be able to do simulation of the part that you want to manufacture. So here for the bracket, you will simulate the stress or the deformation that you're expecting to have during the printing process, and you can even through 3D Expert make a negative of the geometry in order to grow into the deformed so the part will deform into the nominal dimensions. So again, 3D Expert is used really as a design tool. No? So you have all the CAD palette that you would need, and here you can see it on the bracket, where the bracket is modified in order to basically be as support free as possible, and all these stages can be done inside of the 3D Expert software. So once this design side has been done, so we can do all the preparation for the printing process. So this, of course, in the case of metal AM, means adding the support structures, because in a lot of cases you will need support structures for metal AM parts. But this also means that you will be able, and very early on in these stages, to optimize the part for the complete manufacturing chain. So what it means here is that we're already adding in 3D Expert the machine stock allowances that you will need to finish the part. You will have also the machining allowance for the EDM wire cut that will come later on in the process chain. So all of this is thought very early, at very early stages in the production chain. So once this part is designed and simulated, the next step is to move into production. In order to move into production here, what we aim to do, and this is really one of the core strengths of GF, is that we're able to use the System 3R tooling. So System 3R is the GF brand that is in charge of manufacturing tooling and automation products. So in this case, we're printing these brackets, and we'll be able to palletize these brackets onto an individual pallet that will be later on handled individually. So what this means essentially is that you have the typical base plate that will be segmented, in this case, into 16 smaller pallets, and these pallets will therefore be much easier to handle because you will be able to handle each one of these individually in the later machining steps. So this is what it looks like, the part on the pallet, and then you can mount this onto here a reference element which enables the automation in later stages. So of course, this is the preparation of the tooling. The tooling will then go into the AM machine, and this is really the core here and the most important stage in our production process, of course. So in particular, we're talking here about two parts which are manufactured in titanium, and as you may know, so titanium is a very reactive material which will react to oxygen, and one of the very nice advantages that we have inside of the DMP Flex 350 is through the use of a vacuum chamber, we're able to achieve very, very low levels of oxygen. So basically what is done inside of the machine is that you do a vacuum cycle before you start the process, and then you backfill it with argon, so it makes it very quick, first of all, to set up the process, but it also means that we're in a very pure environment. And for whoever knows a bit about welding, for example, you're doing that with inert gas covering, and the reason for this is because you want to avoid oxidation of the material, which will then lead to poor mechanical properties of the final part. So through this vacuum process, we're able to achieve a very, very pure environment and very high quality parts. The second element of this machine, which is notable, is the powder bed quality. So what do we mean by powder bed quality? Here you can see it. It's basically how clean your powder bed is, and this will be dictated by how efficient your gas flow is inside of the machine. So inside of the Flex 350, we have a very efficient gas flow, which is managed through a fan that allows you to evacuate basically the fumes into the back of the machine, which enables a very high quality print. Of course, you have process validation tools. So here you can see our DMP monitoring tools, which are composed of DMP Vision and the melt pool. And the melt pool, this is a very important element because we'll we'll come back to that in the post processing tools and in the quality assurance tools. So this data is already gathered very directly inside of the machine. Of course, in order to be able to print high quality parts, this means that you have to have a very robust database of materials. And what has been developed over time on the Flex 350 is, okay, maybe a number of materials that is maybe limited, but with a very high quality set of parameters that enables you to print the best parts possible. And finally, all this goes without saying, and this important is that we aim to guarantee the best operator safety. So this goes, for example, on the Flex 350 with the glove ports that you will be able to use in order to depowder the parts that you will be producing. So now we have talked about the preparation, we have talked about the tooling that went into the machine, we've talked about the printing process. Then we come to the inspection. So what we can do through the inspection tool, basically here it will be through the data that we have gathered through DMP monitoring, so directly inside of the machine, we will be able to re-import this into 3D Expert. And we will be able to analyze the data that was acquired in order to detect potential defects in the part. So what you can see here on the images are basically so it's a flawed program that was given that was input into the machine, and where the spots that you can see in red represent where the software has detected issues. And what is very interesting is that we can correlate what has been detected directly by the software and data that is detected through CT scanning, for example, and we're able to have a very, very high correlation, a very good correlation up to very, very small pores. So this means that, okay, we will maybe not be able to use DMP inspection as the only tool to validate the quality of parts, but this is a very good insurance for people who are running these kinds of machines, where you can run this kind of analysis based virtually on all parts that you produce, and you can be relatively sure of the quality of the parts that you will be producing. Which in the case of CT scanning is not possible, because these are very expensive operations which you cannot. So first of all, the size of the part that you can process is limited, but also it has a very high cost. So here that all the data is gathered during the printing process, so you can do this for virtually no additional cost. So we talked about all the preparation steps, the printing, the analysis of the quality of the parts that you will have printed. So now we have a printed AM part, and the next stages are to finish this part. So as we said, most parts in AM will need to go through some kind of post-processing. So the first step in the post-processing here, in particular when we're talking about machining, is to prepare the CAM program. So if you remember, when I talked about the preparation stage, we said that we were adding all the offsets and the information that was needed for the milling program. So this had a real goal. What we can do actually inside of 3D Expert is to prepare the milling program to finish the parts. So why is this interesting? This is interesting because all the data is easily accessible. So where you have place support structures, where you have milling offset, everything is available inside of the same environment. So it makes it very quick for an operator to prepare a post-processing finishing operation directly inside of the software, which typically could be a lot more complex, because you need to export the part. You don't know where the supports are located. A lot of information is lost on the way. So here we have really a seamless integration in between the different software and actually hardware operations. So we have prepared the post-processing program. So the next step is to machine the part, and here is where the tooling and the palletization that we discussed earlier comes into play. So basically, the different parts are produced on these individual pallets. So this means that we can basically automate all the machining operations that there will be here. So here on the right hand side, what you can see is the pallet changer, actually, with each one of these parts that has been produced, and the post-processing, the milling operation of this part will be done automatically. So you will load your pallet changer with all the parts that need to be machined. You start the cycle, and then the machine will finish each part one after the other in an automated way. So, and of course here you need some, so the geometry that we have here is quite a complex 5-axis geometry. So we make use of our 5-axis milling machines in order to finish the geometry, and in this case with a very high surface finish in the interface in between the bracket and the other elements. So you work with a multiple position pallet changer, the tooling, and the 5-axis capabilities, and you can do an automated post-processing of the parts in series production. The final stage here of our workflow. So we talked just before about basically our standard subtractive milling machines. In addition to that, what we're aiming to develop is also where we see the needs dedicated machines. So this is in particular true with the CUT AM500. So the CUT AM500 is an EDM machine whose goal is to separate the parts from the build plate. And the goal of this machine is really to overcome the limitations of conventional EDM machines for the cutting or the separation process of AM parts. So which are the limitations that we're aiming to overcome here? First element is that we're doing the cutting of these parts in a horizontal cutting motion. Contrary to a vertical cutting motion, and this has a number of advantages. It means that the parts will not fall onto each other. It allows for a much more stable cutting process, and in the end for a more efficient cutting process. The second element is we're aiming for a high cutting rate. So this machine has the separation process of the AM parts needs to be as quick and as efficient as possible. So we're working here with a fast wire EDM machine, which allows to separate these parts in as quick as possible and have the process in a much more cost efficient way than on a conventional EDM machine. So of course this does not come without drawbacks. These machines are less accurate than what you could have in our high-end EDM machines, but for the needs of AM, this is really what you're aiming for. We're not aiming for the highest accuracy possible in this case. We're aiming for an efficient cutting process and a cost-efficient cutting process. And the cost-efficient cutting process, this comes from several elements. So first of all, the machine has a very competitive pricing, in particular for the size of machine. So you can put in parts of 500 times 500 times 500, but also through the consumables that you will have inside of this machine. So we're not working with brass wire. We're working with molybdenum wire, which will be reused. So everything with the goal to have the most cost-efficient cut possible. So here you can see inside of the machine what it looks like. So you will mount the plate inside of the machine. The machine will rotate the parts upside down, and then the wire will come in and cut the parts off the plate. And what is interesting also is that this machine has been designed in a way that it can be automation ready. So you can mount a basket inside of the machine, which allows you to gather all the parts that will have been cut during the cutting process. So what are the benefits of an integrated workflow? So first element, and I think you will have seen that through this presentation, the AM part, so this is the core technology and the most important step, but this is only a fraction of the cost. And if you want to have an optimized production of AM parts, it is not sufficient only to optimize the AM process. You need to optimize the overall chain. So this goes through the software, through all the hardware steps, the tooling steps, and of course the post-processing operations that you will need for the part. So the benefits are clear. It's you have first of all lead time reductions, because when you can move seamlessly from one operation to the next, it will be much more efficient in terms of lead time. Better machine optimization. So we can think about, for example, the automation of the post-processing in the milling machine, so where everything is automated. Automation, of course, of processes, an optimized TCO, so reducing the total cost of ownership of your AM solution. And of course, we're doing this with the optimum quality assurance and traceability. So as I said, AM is only one fraction of the cost. So here you can see a small split where you can see that AM is more or less, okay, it depends, of course, on what material you're working with and what the exact component is, but it will be between, let's say, 25 and 50% of the cost, and all the rest of the cost will be associated to the preparation, so the CAM preparation, the quality assurance, the finishing, and of course one element that we did not talk about, but the heat treatment of the different parts. So really what we encourage you to do, and this was, let's say, the scope of this presentation, is to not only think about your AM process and of the AM machine for the production of your parts, but to think about this in a holistic way, where you're taking into account the design of your parts, the finishing of your parts, and of course the complete automation and everything that can be input in order to increase the efficiency of your production process. So that was all for my presentation. So I think we can now maybe move to a few questions.
Yeah, absolutely. Thank you so much, Roman. We're very grateful that you could join us today from the TU, and it was nice to see a complete overview of the complete workflow system. It's pretty impressive. So yeah, like you said, I think that it's appropriate to open up the floor for questions. You can also utilize the chat box in the upper right-hand corner of your screen if you would like to initiate any questions that way as well.
as we're waiting for some of those to come through, Roman, it might be interesting to visit about the in-process quality metrics that are able to be used. So as you were showing that slide that kind of detailed the flaws that we're able to pick up in a build as that progresses, could you maybe offer a bit more information on that? That's something that customers of mine have expressed a great deal of interest in the ability to determine those in process. Would you mind doing a bit more there?
Yeah. So basically, to come back on this, on the monitoring and the quality stages. So essentially, what we're doing, so during the printing process, what we're able to do is that we have a product called DMP monitoring, and one of the elements of this DMP monitoring tool is DMP melt pool. So that's what you can see here, actually on the small picture at the bottom here, on the right-hand side. And essentially, what we're doing during this DMP melt pool stage is that we're measuring the reflected light that there is inside of the process, and this allows us, through the variations of this reflected light, to detect issues or areas where there may be potential issues. And what we're doing is, once we have acquired this data, then this data is sent back into 3D Expert, where it is analyzed, and this allows you to detect where there may be flaws in the geometry of the part that you have manufactured. And this is what okay, here these flaws have been forced with a suboptimal process, but these will be detected in the part. So what we're doing is that we're acquiring the data in real time. However, the analysis of the data is offline. So we're currently not able yet to react in line with the process and correct the process live. But what we're able to do is and which is already a very big piece of information, is to detect whether a part is whether we believe that the part is of a good quality or not later on in the process chain, which up to now is a very tricky and often costly operation to go through.
Yeah, thank you very much for that explanation. We had a question come up in the chat. Someone asking, what is the TCO, or total cost of ownership, of the machine? Could you maybe go into a little bit of detail once a machine is installed, specifically I'm assuming the 3D printer, kind of what the associated run costs of that would be, taking into account like the vacuum environment, so argon consumption, things like that.
Yeah. So the TCO, so this is okay, total cost of ownership or total cost of operation. There are different names and definitions that are given, but essentially what TCO is what is the overall cost that you have in order to run a machine. And by running a machine, this is maybe actually not fully correct, because it takes into account also the preparation stages, which you could argue are not really linked directly to the machine. But essentially, if you want to have the most efficient process and the most cost-effective process, you want to optimize your TCO. So this means as we discussed, so this means optimizing the printing stage, and this can be done through the vacuum cycle that we have, where we're able to ensure a very high quality process and consume very little argon. So this will be the consumables basically. This is also linked to the quality, because if you have a lot of scrap, then the quality that, or the TCO, that your total cost of ownership will increase. And then this also goes into the efficiency of your handling of your parts. So it is often difficult to put a number on that, but lead time has a real cost, and being able to handle a part in a very efficient way, this will allow you to manufacture your parts in an optimized way, and therefore optimize your lead time and the reaction that you have with your customers, and reduce your cost basically.
Thank you very much. Could you perhaps speak a bit on the CUT AM500? So do we have a time justification that fast wire technology would typically save on your average build plate versus traditional EDM technology?
Yeah, so for EDM, it's always difficult to give an upfront number because this will depend on a number of parameters. So I'm always a bit skeptical of giving numbers like that. But basically, what we have seen in tests is that we're up to 3 times faster with the CUT AM 500 relative to conventional EDM machines. No, and if you add to this the fact that okay, the machine cost is lower than one of our typical EDM machines, and that the consumables, so per let's say the spool of wire may be more expensive, but you can use it for more time. So the consumables per cut will be lower. It gives you in the end a very efficient cutting process.
Thank you very much. What about power recycling or reclamation? Is that anything that we have technology to embrace? I'm sorry, I misread that. Powder.
Sorry,
powder.
I lost you there for a second. Can you repeat?
Powder reclamation and recycling, not power. I need my glasses. My apologies.
So I still did not get it. I assume your question was around the powder recycling inside of the machine, correct?
Yes.
Okay. So yes, maybe. So I don't have this specifically here on one of the slides, but I can explain this. The concept behind this. So there are different the DMP 350 you can have in different versions. So we have the DMP Flex 350, which allows you to handle the powder. So it's the version that gives you the most flexibility. And so what you will do is that the powder recycling and sieving will be done externally, so on the high performance sieving system. And basically what you will do is that when the process is finished, then the operator will use the gloves in order to remove the powder from the part. This powder will then be full into containers on the sides, and this container will then be moved to the high performance sieving system for the sieving process, and then it can be brought back once it is sieved. So that is the DMP Flex 350, and the interest of the Flex 350 is that it makes it very versatile for customers that want to handle different materials. They can switch the RPM that's inside of the machine, so the removable print module, and they can have 1 RPM per material. On the other hand, you have the DMP Factory 350. So essentially, the printing module is equivalent. What will vary is the powder handling of the powder. So instead of doing this on an external unit on the DMP Factory 350, the powder will be sucked out of the machine, recycled, sieved on the powder management unit, and then you will refill the machine with the sieved powder. So all of this is done with the door shut, so the door does not need to be opened. Of course, it allows obviously for a high efficiency. The limitation here that we will have is that this is not so friendly for material changes. So it means that your machine will be dedicated to one material, which is typically in production processes what is done. Machines are dedicated to one machine, and they're not in series production. Sorry, they're not changed too often. So in particular, if we talk about the 2 examples that we had here today, which are the spinal cages and the brackets. You cannot easily in these regulated sectors change materials, and that's where the DMP Factory 350 comes into play.
Thank you very much. One other question that came up in chat: is there any indication or plans to combine additive manufacturing, 3D printing, and machining on one platform?
So that's a good question. I think that what is important. So let me just come back to the slide here, which illustrates this well. Basically, our position and our ideology is that we believe that it is not efficient to have an AM machine with the milling capabilities or the subtractive capabilities combined. The reason for that is because and this is, I think, often what is seen for hybrid machines, is that you basically get the worst of both worlds. So here you will have an AM machine which is has more hardware in it that has less flexibility, etc. And for the milling process, you will have a milling machine where you cannot use coolant, where the chips are a big problem, so it leads to a lot of issues. So although it may seem on the face of it like a very good solution, when you dig deep and in practice, it's not such an appealing solution after all. So the vision of GF is, instead of combining the two technologies into the same machine, the vision is more to use the most efficient machine for each stage of the process, and to make the links in between the different stages as seamless as possible. So if we want to try and make it in such a way that you will shift from the AM to the milling to the cutting in a very easy way, and you will have always the most adapted machine for the operation that you have at hand. So not combining everything into the same machine, but making the individual machines communicate and work in harmony as best as possible.
Yeah, so kind of focusing a little bit more on the entirety of the process instead of
exactly.
The.
And this means also, for example, we touched upon this with this. This means using our portfolio of standard machines. So through the milling machines, the EDM machines, etc. But it means also making use of the dedicated, so making dedicated machines where we see that the needs of AM are not covered fully.
Great. And to build on something that you mentioned a bit earlier, so for the DMP Flex and the DMP factory configurations, on the Flex machine, what is your typical material changeover time? So if you need to go from aluminum to titanium in that machine, what are we seeing for anticipated changeover times? And to build on that, what is our typical, on our factory machine, the time to switch between jobs? So to go from one build plate to the next.
So this was for the DMP factory 350?
So the changing over of the powder on the Flex and the changing over of the build plates on the factory.
Yeah. Okay, so yeah, just to come back on that again. So on the factory, really the scope is not to change material. So this can be done, but it is really not on a regular basis. So on the Flex 350, here you have the advantage of having the possibility to switch RPMs. So what does this mean is that and this is what we're doing in a day-to-day basis on machines that we have in our customer, in our centers of competence, is that okay, a customer always wants a different material for his sample parts, etc. So what we do is that we have an RPM that is dedicated to one material, or to a class of materials is more often what is done. So if you're talking about, for example, steels and Inconels, here you can use the same RPM once it is cleaned, and then one for aluminium alloys, etc. And what this allows you to do is that you, instead of needing to clean completely the RPM, you will switch the RPMs in between the builds, and this can be done. Okay, it's a very quick process, so it's a matter of minutes that you can do this. Then the internals of the machine need to be cleaned, but these are very easily accessible. So whereas this would take multiple hours on competitor machines, we're able to do that really in a matter of minutes. And it's switching rolling the old RPM out, putting the new RPM in, and you're ready to go.
And just to remind everyone, RPM means removable print module. And that's kind of a key part of these technologies. Sorry, just for clarification. Could you go into a little bit more detail, perhaps on the factory 350 and factory 500 solutions on the depowdering process and powder recycling processes?
Yeah, so on the factory 350, the way it works essentially is that you will, so once the process is finished, so I don't have a very good illustration in this presentation, but I can explain the concept. So inside of the factory 350, what you will have is that the operator will be able to put his hands inside of the glove ports here. And then he has a suction device that allows him to suck all the material out of the build plate and all the remaining powder. Then this powder will be sent to a silo that is at the top of the machine. And then from this silo, the powder will go down again by gravity into a sieving device in order to refill the machine. So for the operator, it's basically you put your hands into the glove ports. All the material is sucked into the silo at the top of the machine. From the silo, it goes down by gravity into a sieve, and in order to refill the machine.
So the factory solution allows the operator to be kind of one step removed from the powder. Most of that's just done internally. Is that a good way to put that?
Yes, so it's everything is included. So the footprint of the machine is equivalent. So you have the same footprint of the machine, and then the sieving and the powder management devices are mounted on top of the machine. So everything
they're all self-contained.
Everything is above. Exactly. Yeah.
Yeah. Okay. There was a question about volumetric accuracy of the build volume. Could you maybe go into a bit of detail on how accurate the parts are when they're removed from the build?
The accuracy of the parts that we can build, or did I understand correctly?
Yes.
Okay, so this is basically a question that is impossible to answer. The reason is because it depends. So basically, this is also let's say something that is particular to additive manufacturing. And the reason is that because in a milling machine, we're able to quantify this quite easily. We can say, okay, the accuracy of my machine is, I don't know, plus minus 1 micron or 5 micron or whatever. Inside of an AM machine, actually, what makes the accuracy of the part is not the hardware, or it's not only the hardware, meaning that there is a very high influence of the geometry of the part that you are printing. And inside of the AM process, you will face deformations. So this means that we can be as accurate as plus minus 20 micron. So sorry, I don't know what that is in inches, but we can be relatively accurate for small parts and parts that do not deform too much. However, if you have a part that is very prone to deformation, then you can have extreme deformation during the printing process, up to, I don't know, one millimeter if in the most extreme cases. So we cannot give a definite figure of the accuracy that you will achieve on the parts that you will be producing. It depends on the geometry. What I can say is that, and this comes back a bit to the software, what we are able to do is we are able to simulate inside of 3D Expert and to estimate what the deformations will be, which allows you to correct beforehand the model of the part in order to anticipate these deformations and deform essentially to the nominal geometry. And this will, so this accuracy topic, this will be true for all AM machine manufacturers. So when a typical accuracy figure is given, this is often given in the best case scenario, but it will really depend. The truth is that it will really depend on the geometry of the part that you will have.
Thank you very much. And I would just note as kind of supplementary information, when we're combating part deformation, sometimes it's worth looking at the ability to palletize your build. So as he illustrated earlier, being able to break up that build plate into many small plates that are significantly more rigid on their own, as that product then flows downstream, that can aid a lot with build accuracy over time. Have another question from an attendee. Do we have a powder consumption value for the manufacture of the satellite bracket that you've been showing, and an estimate on what the cost of that powder may be?
Sorry, I lost you there. Could you repeat?
Sure. Do you have a powder consumption value for the satellite bracket that is shown, and an estimate for the cost of that powder required to build?
Do I have the cost of the powder? So sorry, I don't have the exact figures in mind anymore for that that part. So I believe that we can produce the whole plate in something like a little over a day. So that and then if you multiply that by the average hourly rate, let's say it's about, I don't know, $20 to $40 depending on what configuration you have. So I would say it's more or less 24 times 24 times 40 if we want to maximize a bit. That would be more or less the cost of the manufacturing of 16 of these brackets.
Okay, and it's also worth noting, anybody curious about part cost, please reach out to our staff here in North America. We're delighted to help define designs and cost on a little bit more accurate basis than spitballing, I think I would say.
Yes. So
this
this is one of the very maybe to bounce back on that element. That's one of the very interesting elements of AM. So we're able to simulate the time that it takes with a quite high accuracy, which allows us to give very good figures in terms of what the cost of the manufacturing of a part will be. No.
Right. Here's another one for you. Other than the medical and aerospace industries, which have been kind of leading the charge in the development of additive manufacturing processes, what other industries do you feel are starting to really take a look at additive manufacturing?
Sorry, could you repeat that? I lost you there for a second.
Certainly. Aside from aerospace and medical, what other industries do you find are looking very closely at AM for a technology?
So aside from medical, what other industries are moving into AM? So I think okay, there is so medical is one of the sectors where the gains were most obvious, and it's really let's say a no-brainer to go into additive. I think now we see more and more people adopting additive in many different sectors. So one of the sectors that is growing a lot is energy. So for the production, especially in terms of nickel superalloys, for the production of different components that go into gas turbines, there are big gains. We see also adoption in terms of industry. There are a lot of different segments that are using AM for the production of complex parts that and typically this is in the assembly consolidation. So if you're thinking, for example, of the manufacturing of a machine where you have an assembly of multiple different components, you will move that from the assembly of multiple different components into a single component. So machine building. What else is there that is in growth? So I think that virtually there are a lot of applications out there. The question is how to identify where the highest potential is and get to a sufficiently mature level and order to implement that and take also the risk to implement that. That is often what is limiting companies, where they do not want to take the risk in order to move in, because they're afraid of that they will not manage to benefit sufficiently from the technology. But what we realize is that those who do take the risk, they're able to find a lot of different applications inside of their company, and things that they were not thinking about initially. So that's often what the message that we get from customers is that they find new applications as they go along, and once they have included the technology into their company, then they have a lot more new they have a lot more new applications and case studies that they can put together.
Thank you very much. Some other question here. With conformal cooling, the conversation, this is for plastic injection molding. So with conformal cooling, the conversation seems to be wrapped around reduced cycle time. What other added benefits can it bring to a molding process?
So for conformal cooling, and then I missed the end of the question.
Yeah, aside from reducing cycle time, what other benefits could it bring to the injection molding process?
So I think, okay, cycle time is one element. The main, one other very important element is, and this will be linked in the end to cycle time, is the quality of the plastic part. Because if you have a more homogeneous temperature distribution or temperature gradient on the part that you're manufacturing, or the plastic part that you're injecting, then you will have less warping and distortion once you have injected the part now. So quality of the plastic part, this is a very important driver. Then what we have seen also in terms of advantages in running the mold, this can also be linked to the reliability of the mold, and this is in particular true for pressure die casting. So in pressure die casting, you're at very high temperatures, and you have molds where the cooling is achieved through the assembly of multiple different elements, where there are seals that hold the different parts together. And when you're soliciting these at high temperatures, then the seals often fail, and this can lead to downtown of the mold, etc. So it can increase the reliability of the mold that you will have, so less chance of cooling seal failures. What else is there? I think that these are the most obvious ones. No?
Thank you very much. With that, I think we are out of time. I'll hand it over to Lindsay Lewis.
Yeah, thank you, John, and thank you to those that participated and asked some questions. You guys asked some really good ones. I think there are also a couple more, maybe diving into some of the details on the powder and the cycle process. I think it might be interesting to maybe even do a follow-up webinar on that whole process. But either way, it was great that everyone got to join us today. We're very thankful for Roman to be able to address some of those questions. So you guys will be sent out a link once this webinar is complete. You guys can view this at a later time. We encourage all of you guys to reach out directly to us. Our contact information will also be sent to you. And then, of course, follow us for future webinar notifications. So until next time, guys, have a wonderful weekend.